NOTMAD, Estimating Bayesian Networks with Sample-Specific Structures and Parameters. Ben Lengerich *1, 2, Caleb Ellington 3, Bryon Aragam4, Eric P. Singh 3, 5, and Manolis Kellis1, 2. 1 Massachusetts Institute of Technology 2 Broad Institute of MIT and Harvard 3 Carnegie Mellon University 4 University of Chicago 5 Mohammed bin Zayed University of Artificial Intelligence November 2, 2021 Abstract Context-specific Bayesian Networks, i.e. directed acyclic graphs, DAGs, identify context-dependent relationships between variables, but the non-convexity induced by the acyclicity requirement makes it difficult to share information between context-specific estimators, for example with graph generator functions. For this reason, existing methods for inferring context-specific Bayesian networks have favored breaking datasets into subsamples, limiting statistical power and resolution, and preventing the use of multidimensional and latent contexts. To overcome this challenge, we propose NOTEARS-optimized mixtures of archetypal DAGs, NOTMAD. NOTMAD models context-specific Bayesian networks as the output of a function which learns to mix archetypal networks according to sample context. The archetypal networks are estimated jointly with the context-specific networks and do not require any prior knowledge. We encode the acyclicity constraint as a smooth regularization loss which is back-propagated to the mixing function. In this way, NOTMAD shares information between context-specific acyclic graphs, enabling the estimation of Bayesian network structures and parameters at even single-sample resolution. We demonstrate the utility of NOTMAD in sample-specific network inference through analysis and experiments, including patient-specific gene expression networks which correspond to morphological variation in cancer. 1. Introduction. Estimating the structure and parameters of Bayesian networks, BNs, is a classic problem in which we seek to summarize relationships between variables by factorizing the joint distribution as a probabilistic graphical model. This approach has been applied to many problems in biology, 34, genetics, 45, machine learning, 22, and causal inference, 38. However, the relationships between variables are often non-stationary and context-specific. Previous attempts to model these context-specific relationships, such as time-varying networks, 3, 31, 37, have enjoyed success in estimating network connections which vary according to a single observed axis of variation, for example time. However, when dealing with complex processes which vary according to many processes simultaneously, we often do not know a priori how observed covariates relate to network structure. Thus, we would like a method which can estimate BNs with structures and coefficients that vary according to several, and possibly latent, continuous factors. Such a method would enable us to understand large, heterogeneous datasets as directed relationships which rewire in continuously changing contexts. Toward this end, we propose NOTEARS-optimized mixtures of archetypal DAGs, NOTMAD, a framework for network estimation which views BNs as the output of a learnable function of sample context. There are two main challenges is designing such a method. How can we enforce acyclicity, traditionally expressed as *Lengerich at mit.edu1 R14:2111.01104v1, stat.ml November 1, 2021 Figure 1, our motivating example, patient-specific network inference for understanding cancer at high resolution. We know that each patient's tumor is uniquely shaped by genetic and environmental factors. We would like to summarize the gene regulatory relationships in each tumor as a BN to identify mutations and therapeutic targets. However, the assays which measure gene expression destroy the tissue sample, so traditional methods of network inference which treat networks in isolation are unable to estimate patient-specific networks. Our framework instead views each network as the output of a function of patient-specific covariates, which can be used to predict the patient's gene network as a personalized mixing of archetypal networks. In this view, the generative function of regulatory networks is shared between many patients and can be learned efficiently, even when we have only a single sample from each patient. A combinatorial constraint, on the output of a learned function, and how should we encode latent network structure in a learnable function? Our key insight is that acyclicity function can be imposed as a smooth regularization loss on the graph generator, allowing context-specific networks to be modeled as mixtures of archetypal DAGs. As a result, NOTMAD is able to generate context-specific Bayesians at single-sample resolution, allowing us to ask new questions regarding sample heterogeneity and latent structure. Motivating example: gene regulatory network inference for personalized cancer analysis. A common task in bioinformatics is to infer regulatory networks from gene expression data. That is, we seek a graphical model which factorizes the distribution of gene expression, from which we can infer regulatory relationships. This graphical model representation is especially useful for cancer analysis. Cancer is a highly individualized disease, 28, for which distinct biological processes are important for understanding and treating different tumors. Moreover, cluster-based analyses are limited because tumors may not form discrete clusters, 42. Thus, we seek patient-specific Bayesians to identify dysregulated pathways in therapeutic targets at patient-specific granularity. However, bulk RNA sequencing assays which measure gene expression destroy the physical sample. As a result, we are given only a single instance from which to view each tumor. Thus, traditional methods to estimate Bayesians by clustering samples are incapable of providing patient-specific inferences. In this paper, we develop a method, Figure 1, which views Bayesians as the output of a learnable function of contextual patient information. This enables us to estimate personalized gene regulatory networks, and perform personalized analysis of cancer patients while sharing statistical power between many samples. Contributions: this paper contributes NOTMAD, a method for estimating context-specific Bayesians which enables sample-specific network inference, enabling analyses of network heterogeneity. Underlying NOTMAD is a meta-view of structured models in which parameters are outputs of a shared, learnable graph generator function. Previously, it was thought that the structured aspect of these models prohibited graph generator functions. We show that these structured models, for example context-specific Bayesians, can be efficiently modeled as interpolations between a small number of latent archetypes, and the non-convexity of the model domain can be enforced with regularization. This perspective unites two areas of recent interest in machine learning: structure learning and contextualization. Python code of NOTMAD is available at https://github.com/knellington/sample-specific DAGs. 2 Preliminaries. DAG structure learning. The basic DAG learning problem is formulated as: let xrn times p be a data matrix consisting of n observations of the random vector x equals x1, xp. Let D denote the space of DAGs G equals v, e, of p nodes. Given x, we seek weighted adjacency matrix WRP times P, which defines a DAG GD with structure defined by the binarized adjacency matrix a W, where a Wij equals 1 Vi does not equal 0, and describes the joint distribution Px via a structural equation model. 22, 38. Structural equation models. To translate the weighted adjacency matrix WRP times P into a joint distribution on X, we use a structural equation model, SEM. Linear SEM models xj equals weight jx plus j, where x equals x1, xp, is a random vector and equals 1, p, is a random noise vector. This form can be modified to use more flexible transition functions with exj spa xj equals fwj, x. For example, for Boolean xj, we can use a logistic link function. For the remainder of this paper, we will assume linear SEM with Gaussian and drop this specification. However, we note that NOTMAD easily extends to other SEM by replacing this portion of loss function. Thus, a DAG W defines a Bayesian network, Bn, distribution Bn(x)W, which provides the likelihood of observing x under structure W and imposes least squares loss W, x, equals 1 to n x minus xw2f. 3. Inferring context-specific Bayesian networks. 3.1 Problem definition. We are interested in learning Bayesians which are context-specific, i.e., the parameters and/or structure of the Bayesians may vary according to context. In this problem, for each observation XRP, we also observe contextual data CRM. We can describe this as factorizing Px, C, equals WDWPX WPWCPC, where PXW equals BNXW, recalling BNW was defined previously as the distribution implied by Bayesian structure W. Drawing back to the motivating example discussed in Section 1, we can view X as gene expression, W as a gene regulatory network, and C as patient covariates which contextualize the network. This is similar to a varying coefficient, VC, description of Bayesians, which would model W equals FC with some learnable F. However, it is not tractable in practice to estimate context-specific Bayesians using this VC form because DAGs are high-dimensional and DAG space is non-convex, so defining F to generate DAGs is unsolved. We are particularly interested in the extreme case where there is at most one observation per context, i.e. sample-specific Bayesians. In such cases, there is limited power to infer each Bayesian. This differs from other applications in we many samples per context. For example, C is discrete and takes on finitely many values, and cluster-based models may succeed. In the most challenging setting of sample-specific inference, we require a tool to share power between sample-specific estimators. 3.2 Our approach, smooth network inference and contextualization as described above. The main challenge in inference of context-specific Bayesians is that W is a high-dimensional, structured latent variable which must satisfy acyclicity. To overcome this challenge, we assume that context-specific Bayesians lie on a subspace measured by a latent variable ZRK such that C, X, W, Z. A graphical diagram of this meta-model is shown in Figure 2. Drawing back to the motivating example, we can imagine that tumors correspond to latent molecular subtypes, 24, 44, and mutations Z which govern the underlying gene regulatory functions W. This conditional independence implies that knowing the patient covariates C would not give any additional insight into the gene expression values X if either the molecular subtype or the graph structure W were already known. With this meta-model, PWX, C, PXWZ DZ PWZ PZC, where PXW equals B and XW, and our challenge reduces to defining tractable PWZ and PZC. In NOTMAD, we use a smooth DAG criterion to define PWZ and use contextual parameter generation to estimate latent Z to generate W. In this way, our approach to context-specific network inference builds on two developing themes in machine learning: smooth DAG inference and contextual parameter generation. 3CZWX Figure 2, Graphical Model. Contextual covariates C and observations X are observed, while subtype Z and Bayesian parameters W are latent. Smooth DAG inference via NOTEARS estimating DAG structure, even for a single population model, from data is NP-hard, 9, largely due to the acyclicity constraint which has traditionally been formulated as a combinatorial optimization. Recent work, 46, however, has translated this combinatorial optimization into a continuous program through the matrix exponential, HW equals TREWW, minus P equals 0 WD, whereas the Audemars product and EA is the matrix exponential of A. This expression of acyclicity is useful because HW has a simple gradient, HW equals EWW, T2 watts. In NOTMAD, we relax HW into a regularizer which is backpropagated for gradient-based training. Contextual parameter generation. As datasets continue to increase in size and complexity, sample-specific inference has driven interest in many application areas, 2, 6, 12, 17, 29. Several frameworks have been proposed to estimate meta-models which use contextual information C to generate model parameters theta. In general, we can write the operation of these frameworks as theta equals ZTQ, where Z equals G phi, C, This form encompasses several well-known framework of contextualized models. If G is a linear model and Q is an identity matrix, we have the varying coefficients model. 18. If G indexes the k nearest neighbors in Q by a learned distance metric on C, we have personalized regression. 26. If G is a deep neural network and Z equals 1, we have contextual explanation networks. 4. If G is a few steps of gradient descent beginning at the initialization phi for the instances grouped by C, we have meta-learning. 11. 36. In NOTMAD, Q is a learned dictionary of DAG archetypes and G is a differentiable context encoder. Details in sec.4. 3.3 Related work. This problem of estimating sample-specific Bayesians has its roots in context-specific independence, CSI 5, which permitted that the independence relations captured in Bayesian sparsity patterns may hold only for certain contexts. In general, CSI transforms the traditional Bayesian DAG into a multi-graph. A long line of work have invested into developing alternative representations and approaches for estimating CSIs. 10, 14, 30, 32, and more recent approaches have used causality rules to perform instance-specific independence tests. 19 to 21. However, these approaches rely on the combinatorial view of acyclicity and hence suffer scalability challenges. There have also been approaches to design estimators of multiple Bayesians without sample-specific covariates. These frameworks include priors governing network rewiring, 15, 25, and sample-specific networks as deviations from a population network, 23. For example, Linus, 23, estimates linear network for sample I as the weighted difference between the network estimated by all n samples and the network estimated by n-1 samples, leaving out the ith sample. While this approach showcases the clever idea of the exchangeability of these estimators and differences in linear SEM, it does not share statistical power between sample estimators. The statistical power is only shared for the population model. A similar approach was used to identify sample-specific dysregulated pathways in a gene regulatory network by examining the residual of neighborhood regressions. 7. Although this approach was more robust than the above because it sought only to estimate dysregulation rather than the underlying network. There are fundamental limits to the estimation of populations of parameters without any covariate information. 43. For this reason, we concern ourselves only with the setting where we observe covariate information to contextualize the Bayesian. Finally, we are not the first to study mixtures of archetypal DAGs. Past methods have focused on estimating the latent mixture subtype of a population, 40, 41, or of individual samples, 35. However, these methods use localized structure search algorithms, which creates a computational bottleneck that constrains learning to only mixing a predefined set of archetypal DAGs. This severely hinders the adaptability of these models because it requires a perfect prior knowledge about the causal structures underlying DAG mixtures. In contrast, NOTMAD uses smooth optimization to learn archetypal DAGs without any prior knowledge. For NOTMAD, NOTEARS-optimized mixtures of archetypal DAGs to estimate sample-specific Bayesians, we propose NOTMAD, which represents context-specific distributions as Pxc equals Bnx phi theta, c, 1, which equates to x equals phi theta, c, tx plus under the linear SEM, where is a noise vector. Context-specific DAGs w equals phi theta, c, are generated by phi theta as a convex combination of a fixed number, k, of archetypal DAGs, w1 k, w equals phi theta, c, equals k equals 1 sigma, f theta, ck, wk, 1 minus I, 2, where sigma is the softmax function and f theta is the context encoder, a learned function parameterized by theta. The softmax constraint ensures that the weighting of each archetype is positive and sums to 1, permitting these values to be interpreted as the probability of class membership. The dictionary of archetypal DAGs, w1 k, is estimated jointly with the context encoder f, and the entire architecture is trained end-to-end. Finally, we clamp the diagonal of each wk to 0 to avoid the cyclic w equals I. To ensure that each w is acyclic, we balance the estimation loss with the NOTEARS-optimized loss hw. Thus, NOTMAD can be summarized as the following minimizer: argmin theta, w1 colon kni equals 1, xi minus xi phi theta, ci, 2 plus alpha tr, e phi theta, ci phi theta, ci, plus kk equals 1 beta wk 1 plus gamma tr, e wk wk, 3, where alpha, beta and gamma are hyperparameters that trade off predictive loss against DAGs and sparsity, and we recall that hw equals treww is the acyclicity regularizer discussed in section 3.2, here applied to both the context-specific and the archetypal DAGs. As introduced in Sec. 3.2, NOTMAD has a natural probabilistic interpretation. We have defined EPWZ equals KZKWK, 1 minus I, and constrained Z, QRK greater than or equal to 0 colon Q equals 1, by Z equals sigma, F theta, C, such that these weightings are a convex combination. Python code of NOTMAD is available at https://github.com/knellington/sample-specific DAGs. Context encoder. This definition of NOTMAD is flexible with respect to the form of the context encoder f. Any differentiable function can be used. We have found best success and report all experimental results using a neural additive model, 1, which rivals the accuracy of fully connected neural networks while retaining interpretability. For other types of contextual data, other encoder models may be more appropriate, for example a convolutional neural network for images. Fine-tuning the NOTEARS regularizer encourages the context encoder to produce acyclic graphs. However, we are not guaranteed that the graph predicted by NOTMAD will be acyclic for all unseen test contexts. Nevertheless, any directed graph can be projected to a DAG by removing edges which violate acyclicity. For fixed W, we perform a binary search over the magnitudes in W to find the minimum value T for which W greater than T, equals WD. This produces a DAG W, to which we attempt to add back excluded edges from W in order of decreasing magnitude of edge weights, checking that each edge addition does not form a cycle. In practice, predictions from NOTMAD do not require fine-tuning beyond thresholding out weak edges. Benefits of modeling networks as mixtures of archetypes. In some sense, NOTMAD is comparable to a multi-output varying coefficients model with an extra loss to encourage acyclicity. However, NOTMAD uses archetype mixing to create a bottleneck and reduce the effective dimensionality of the outputs, borrowing the dictionary learning framework of 4. This bottleneck has statistical benefits, constraining the sample-specific DAGs to lie in a k-dimensional polytope defined with the k archetypes as extreme points. In addition, this has computational benefits. It is not tractable to store many p times p matrices in memory. The archetype view allows efficient computation and optimization. Finally, archetypes aid interpretability. We can understand latent membership patterns by visualizing the context subtype mapping in the additive context encoder F theta. 5. Non-convexity. Is it reasonable to define sample-specific DAGs as convex combinations of archetypal DAGs? The DAG constraint is non-convex, so it is not true that the convex combination of any set of DAG archetypes would be acyclic. If DAG space is highly disconnected, then we should not expect optimization to efficiently learn to generate DAGs by combining archetypal DAGs. Is NOTMAD hopeless? Inspecting the topology of DAG space gives hope. The compatibility of DAGs is driven by the sparsity structure of summons, not the weighting. Let a W be the binarized structure of W, i.e. a Wij equals 1 Vi does not equal 0. Then a W1 plus a W2D all 1 plus W2DA. Conversely, if a W1 plus a W2D, then all 1 plus W2D for at most P2 values of A. As a result, there is minimal confusion over allowable archetype combinations. Either the combination is acyclic for all weightings, or there is a small, finite set of weightings which produce DAGs, and all other weightings produce cyclic graphs. Thus, the context encoder F needs only to learn compatible archetypes, not compatible weightings. 5 experiments Bayesians factorize joint distributions into tractable conditional dependencies, thus inference of context-specific Bayesians provides insight into the changing dependencies and heterogeneous data. Traditionally, structure learning has required multiple observations for each network. In contrast, NOTMAD enables us to estimate sample-specific networks for unclustered individual observations. Here, we evaluate the success and limitations of NOTMAD to identify the accuracy and utility of sample-specific network inference. Baselines: we compare the performance of NOTMAD against estimators of Bayesians at various resolutions. State-of-the-art population estimator, NOTEARS-46, a cluster-specific estimator which first clusters the samples according to the context and then applies the population estimator to each cluster, and sample-specific Bayesian inference by Linus, 23. Finally, when we have domain knowledge regarding latent sample structure, we construct Oracle-clustered estimators by clustering the samples according to domain knowledge and applying the population estimator to each cluster. On real data, we do not have access to the underlying Bayesian, thus, we evaluate the mean squared error, MSE, of x minus xw2 on held-out samples, which corresponds to the likelihood of the observed data under the probabilistic interpretation of the linear SEM. 5.1 Finance. Finally, we explore heterogeneity in a dataset of financial asset prices and news headlines from 26. This dataset was proposed to show the utility of allowing regression parameters to change over time and industry. Here we examine how the interrelatedness of the samples drifts over time by estimating contextualized Bayesians. For each date, we have as context C a summary of the news headlines as a 50-dimensional vector, while the predictors X are the trading price of 24 assets. We split the 14,555 samples into train/test sets at the 75th percentile date, which is approximately the beginning of 2011, to produce a training set of 10,916 samples. From these data, we estimate daily Bayesians of asset price relations contextualized by history and news. In addition to giving the best MSE loss on held-out samples, Table 1, the estimated Bayesians show interpretable patterns. As shown in Figure 3, the sample-specific networks accurately translate the changing environment into interpretable networks of financial relationships. Dataset population clustered Oracle clustered Linus NOTMAD Finance 0.58 plus or minus 0.01 0.54 plus or minus 0.01 0.67 plus or minus 1.94 0.43 plus or minus 0.008 football 0.47 plus or minus 0.006 0.44 plus or minus 0.006 0.41 plus or minus 0.004 0.52 plus or minus 0.19 0.35 plus or minus 0.005 Cancer 0.49 plus or minus 2.3 E minus 5 0.37 plus or minus 6.5 E minus 4 0.24 plus or minus 1.1 E minus 4 0.65 plus or minus 0.14 0.14 plus or minus 2.7 E minus 5 single cell 0.56 plus or minus 0.02 0.45 plus or minus 0.01 0.37 plus or minus 0.02 0.60 plus or minus 0.08 0.28 plus or minus 0.02 Table 1. Mean squared error, MSE, loss of Bayesians applied to held-out samples. Values displayed are the mean plus or minus variance of the MSE over 10 bootstrap samples. No Oracle for clustering. 61970 1980, 1990, 2000, 2010, 2020 Year Network Map 1, A. Embeddings of context-specific Bayesians by date. Context-specific Bayesians recover trends leading to and the broad dislocation after the 2008 financial crisis. 1970, 1980, 1990, 2000, 2010, 2020 year 1970, 1980, 1990, 2000, 2010, 2020 year -0.75, -0.5, -0.25, 0.00, 0.25, 0.5, 0.75 cosine similarity. B. Cosine similarities between context-specific Bayesians by date. Context-specific Bayesians recover macro trends including 1970s stagflation, 2000s growth, and 2008 financial crisis. Figure 3. Representations of context-specific Bayesians estimated for financial asset prices. 5.2 Football. A goal in sports analytics is to isolate the influence of individual players from the abilities of teammates. Professional players are often rated by independent rating agencies. We can use ratings to identify influences by estimating a Bayesian to factorize player ratings. In such a Bayesian, each node represents a player rating while edges represent how the rating of a player is influenced by the ratings of teammates. Context is critical. Team strategies dictate player expectations and analyses. We use ratings 1 of 1,000 professional football players from the 2020 National Football League season. We group players into 7 position categories, and construct simulated observations of lineups by team. For context, we use the team identity and a PCA-reduced representation of the ratings. For oracle clustering, we use team identity. In this dataset, n equals 1,478, with 634 test samples, p equals 7, and m equals 4. As shown in Table 1, context-specific Bayesians capture the distributions of player ratings more accurately than population or cluster-based Bayesians. 5.3 Gene Regulatory Network Inference for Personalized Analysis of Cancer. We now return to the motivating example discussed in Section 1. Dataset. We use bulk RNA-seq gene expression data from the Cancer Genome Atlas 2, TCGA, which measures the average expression of each gene in the patient's tumor. We select 784 RNA-seq transcripts, features, based on annotation in the Cosmic Gene Census, 13, and large variance over the sample. These gene expressions levels are measured for 9,715 patients, which each have 12 contextual covariates: age, gender, race, sample type, primary site, percent stromal cells, percent tumor cells, percent normal cells, percent neutrophil infiltration, percent lymphocyte infiltration, percent monocyte infiltration, and a single principal component of gene expression which captures batch effects in processing. The cancers span 20 tissues and 26 types of tumors. Results: patient-specific Bayesians estimated by NOTMAD represent gene expression better than do population, cluster-specific, or tissue-specific Bayesians. Not only do patient-specific Bayesians improve average MSE, Table 1, the patient-specific Bayesians also improve estimation in every tissue, Figure 4. The largest outperformance is seen for cancers of the lymph nodes. MSE of tissue-specific Bayesians is 4.9x that of NOTMAD. Brain, 2.4x, thyroid, 2.0x, prostate, 1.9x, colon, 1.8x, and head/neck, 1.8x. The high resolution of these patient-specific Bayesians unlocks new investigations of network heterogeneity. For example, are the patient-specific distributions of gene expression best viewed as a patient-specific selection of a distribution, or a patient-specific mixture of archetypal distributions, i.e. do gene regulatory networks in cancer rewire according to a small number of fixed processes, or do they interpolate between processes? With NOTMAD, we can begin to answer this question. Here, we examine this question through an ablation study, constraining each patient-specific Bayesians to use only a single archetype, one archetype in Figure 4, or to use only a single Bayesian for all tumors of a particular tissue average in Figure 4. According to MSE, 1 https://www.lineups.com/NFL/player ratings 2 https://portal.gdc.cancer.gov/7 Figure 4, MSE of Bayesians of gene expression and cancer, grouped by tissue. The number of training samples for each tissue type is provided in parentheses. In addition to the population, cluster-specific, and tissue-specific baselines, we also include ablations of the NOTMAD model. 1 archetype, tissue average uses the power sharing of NOTMAD across tissues, but only estimates a single Bayesian for each tissue. Archetype mixture, tissue average similarly estimates a single Bayesian for each tissue but allows this tissue-specific Bayesian to be a mixture of archetypal DAGs. 1 archetype, sample-specific estimates patient-specific Bayesians that are constrained to use only a single archetype. Archetype mixture, sample-specific is the entire NOTMAD model. The full patient-specific heterogeneity of NOTMAD is required to achieve optimal summarization of gene expression distributions, suggesting that these cancers exhibit a diversity of expression patterns that cannot be resolved by a cancer Bayesian, i.e. a population model, tissue-specific Bayesians, or patient-specific Bayesians which are selections of clustered networks. Instead, tumors as best modeled as interpolations between latent processes. In addition, the patient-specific Bayesians recover medically significant heterogeneity. By inspecting network embeddings, Figure 5, we see that the Bayesians estimated by NOTMAD tend to cluster according to tissue. Nevertheless, the patient-specific Bayesians separate lung adenocarcinoma, LUAD, samples from lung squamous cell carcinomas, LUSC. These subtypes of lung cancer have important distinctions in clinicopathology, e.g. LUSC is associated with the history of smoking, while LUAD is the most common form of lung cancer in non-smokers, 33, and treatment. For example, epidermal growth factor receptor and anaplastic lymphoma kinase are two commonly mutated genes in LUAD and are targets for current therapies, while they are infrequently mutated in LUSC, 27. Since NOTMAD did not have access to this LUAD/LUSC distinction as contextual data, this distinction must be a result of optimizing MSE loss, indicating different regulatory networks underlying these biomedically distinct subtypes of lung cancers. In addition to recovering known heterogeneity of disease types, NOTMAD also identifies intra-disease heterogeneity which correspond to morphological distinctions. For example, the Bayesians for colon cancers tend to be interpolations between two archetypal networks, and similarly head and neck cancers have two archetypal networks underlying the patient-specific Bayesians. For colon cancer, this heterogeneity may correspond to the 4 consensus molecular subtypes, 16, while for head and neck cancers, this split may correspond to differences in head and neck tumors arising from either tobacco use and/or HPV, 39. Whole slide imaging of these tumors, Figure 5, shows the morphological distinctions between the two latent Bayesian archetypes, suggesting a correspondence between gene regulatory network heterogeneity and tumor morphology. 5.4 Single-cell gene regulatory network inference. The gene regulatory network of each brain cell is unique, shaped by its cell type, cell state, history of activation, interconnections, environment, and by the age, sex, and disease status of each person. However, these networks are highly related across cells and highly structured, as they are shaped by circuitry constraints, a limited set of regulatory programs, and a finite set of active regulators. Here, we exploit this structure by using NOTMAD to simultaneously estimate network archetypes and the cell-specific networks using paired epigenetic and transcriptomic data. Importantly, we learn both membership vectors and archetypal networks de novo in an end-to-end joint optimization, in essence inferring a functional transformation that predicts a cell's gene regulatory network from its DNA accessibility profile. 8 OMAP 1 OMAP 2 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 Figure 5, patient-specific Bayesians embedded by OMAP. Top, without access to disease type during training, the patient-specific Bayesians accurately recover heterogeneity between cancers of disparate tissues and cancers of different subtypes affecting the same tissue. Bottom, network archetype selection suggests network heterogeneity in both head and neck squamous cell carcinomas, left, and colon adenocarcinomas, right. For each archetype, we show image patches from the three cases, by row, which maximize NOTMAD activation of the archetype, 10 patches each, and draw arrows to the corresponding sample group containing these cases. Dataset to estimate single-cell regulatory networks. We use recently developed dual assay technology, which allows simultaneous profiling of transcriptomic, RNA-seq, and epigenetic, ADIC-seq, markers in matched single cells. In this example, we use the SNARE-seq dataset of 10,309 cells from adult mouse brain cells, 8. To preprocess the SCRINA-seq, we initial perform quality control with poor quality cell removal and doublet removal. Next, we remove empty droplets using droplet utils and doublets using SCDS with a threshold of 1.0. Finally, we normalize reads with linnorm. Finally, we perform a PCA transform of both the SCATIC-seq and SCRINA-seq data to compress each to 5 covariates. The preprocessed dataset is available at https://github.com/Lengerich/SNARE-seq. Results as shown in Figure 6, cell-specific Bayesians more accurately capture the heterogeneity of gene expression than do cell-type-specific Bayesians, cluster-specific Bayesians, or a single population Bayesian. This benefit is observed for all cell types, with most benefit for cell types which are less common in the training set or more uniquely differentiated due to their biological function, suggesting that NOTMAD improves performance through both sharing power between samples and capturing heterogeneity where appropriate. In addition, the cell-specific networks cluster according to the cell's biological function. Networks for all subtypes of inhibitory neurons cluster together, while networks for all subtypes of excitatory neurons also loosely cluster together. In contrast, networks for OPC, Oli-Mal, Mike, and AST cells do not cluster with either the excitatory or inhibitory neurons. 9 AST, 214, Claustrum, 58, XL2/3 Rascroft2, 1049, XL3/4 RMSD, 62, XL3/4 Rorb, 835, XL4/5 EL1 Ripple2, 286, XL4/5 THSD7A, 401, XL5 Gound14, 373, XL5 Parm1, 165, XL5/6 TSHC2, 35, XL6-4, 627, in P, 113, in PALB, 128, in SST, 88, Mike, 258, OPC, 56, Oli-Mal, 115, unknown, 309, 0.00.5 1.01.5 2.0 2.5 3.0 3.5 4.0 MSC, held out cells, population clustered cell type cell specific, A, mean squared error, MSC, of Bayesians of single cell gene expression. We compare 4 models, 1, a population model which estimates a single Bayesian, 2, a clustered model which estimates a small number of discrete clusters of samples and cluster-specific Bayesians, 3, cell-type-specific networks which a Bayesian for each cell type, and 4, cell-specific networks estimated with NOTMAD. In all cell types, the cell-specific networks estimated by NOTMAD are the most accurate. AMAP1 AMAP2 AST Claustrum XL2/3 Rascroft2 XL3/4 RMSD XL3/4 Rorb XL4/5 EL1 Ripple2 XL4/5 THSD7A XL5 Gound14 XL5 Parm1 XL6-4 NP and PALB and SSD Mike OPC Oli-Mal unknown. B. Network embeddings, colored by cell type. Each point represents the Bayesian for a single cell, embedded with AMAP. The networks for inhibitory and excitatory neurons tend to cluster according to their corresponding type, with subtypes providing a modest subclustering. Astrocytes form a distinct cluster of networks, while Oli-Mol, OPC, and Mike cells form a separate cluster. Ast-claustrum XL2/3 Rascrf2 XL3/4 RMSD XL3/4 Rorb XL4/5 EL1 Ripple 2 XL4/5 THSD7 AXL5 Gaunt 14 XL5 Parm 1 XL5/6 TSHE2 XL6-4 Indian Plauban SSD Mike OPC Oli-Mol unknown cell type Ast-claustrum XL2/3 Rascrf2 XL3/4 RMSD XL3/4 Rorb XL4/5 EL1 Ripple 2 XL4/5 THSD7 AXL5 Gaunt 14 XL5 Parm 1 XL5/6 TSHE2 XL6-4 Indian Plauban SSD Mike OPC Oli-Mol unknown random 1 random 2 random 3 random 4 random 5 random 6 random 7 network archetype 0.1 0.2 0.3 0.4 0.5 archetype probability, C. Network archetype selection by cell type. Color corresponds to the mean weight of each archetype, interpreted as a probability, in constructing cell-specific networks for cells of each cell type. In addition to cell-type-specific network archetypes, we also initialize 7 archetypes to uniformly random sparse networks, random. Excitatory and inhibitory neurons share network archetypes between subclasses, but other cell types use distinct archetypes. Figure 6. Cell-specific networks reveal cell-specific heterogeneity in adult mouse brain. 10.6 Conclusions. We have presented NOTMAD, a method to estimate context-specific Bayesians by learning to transform contextual data into Bayesian parameters. Previously, the structured constraints of Bayesians prohibited graph generator functions. We show that these structured models can be efficiently modeled as interpolations between a small number of latent archetypes, and the non-convexity of the model domain can be enforced with regularization. As a result, NOTMAD enables simultaneous inference of sample-specific and archetypal Bayesians without any prior knowledge of Bayesian structure, parameters, or sample relationships. NOTMAD scales to the extreme case of estimating sample-specific Bayesians, in which each context is observed for only a single statistical sample. Bayesians are a mainstay of analysis in many fields including biology, medicine, social sciences, and beyond. Context-specific Bayesians enable new questions of heterogeneity of latent structure and provide axes of variation which can be used to describe community composition and influences at a new granularity. Acknowledgements. BL was supported by the Alana Fellowship at MIT. CE and EX were supported by NIH NIGMS R01GM140467. BA was supported by NSF EAS 1956330, NIH R01GM140467, and the Robert H. Topol Faculty Research Fund at the University of Chicago Booth School of Business. References: 1. R. Agarwal, L. Melnick, N. Frost, X. Jong, B. Lengerich, R. Caruana, and G. E. Hinton. Neural Additive Models, Interpretable Machine Learning with Neural Nets. R14 preprint R14:2004.13912, 2021. 2. I. A. Jinko, K. A. Doherty, and A. P. Van Cleve. Personalized Lifetime Financial Planning Tool, June 24, 2010. U.S. Patent App. 12316967. 3. A. Ahmed and E. P. Crossing Recovering Time-Varying Networks of Dependencies in Social and Biological Studies. Proceedings of the National Academy of Sciences, 10629, 11878 to 11883, 2009. 4. M. Al-Shedavat, A. Dubey, and E. Crossing Contextual Explanation Networks. Journal of Machine Learning Research, 21 194, 1-44, 2020. 5. C. Boutelier, N. Friedman, M. Goldsmith, and D-color. Context-specific independence in Bayesian networks. R14 preprint R14:1302.3562, 2013. 6. F. Buettner, K. N. Natarajan, F. P. Casal, V. Proserpio, A. Shaldoni, F. J. Thace, S. A. Teichmann, J. C. Marioni, and O. Stegel. Computational analysis of cell-to-cell heterogeneity in single-cell RNA sequencing data reveals hidden subpopulations of cells. Nature Biotechnology, 33 155, 2015. 7. K. L. Busher, M. Shikina, and P. V. Banos. Causal network perturbations for instance-specific analysis of single-cell and disease samples. BioArXiv, page 637710, 2019. 8. S. Chen, B. B. Lake, and K. Zhang. High-throughput sequencing of the transcriptome and chromatin accessibility in the same cell. Nature Biotechnology, 3712, 1452-1457, 2019. 9. D. M. Chickering. Learning Bayesian Networks is NP-complete. In Learning from Data, pages 121-130. Springer, 1996. 10. D. M. Chickering and D. Heckerman. Efficient Approximations for the Marginal Likelihood of Bayesian Networks with Hidden Variables. Machine Learning, 29 2-3, 181-212, 1997. 11. C. Finn, P. Abiel, and S. Levine. Model-agnostic meta-learning for fast adaptation of deep networks. In International Conference on Machine Learning, pages 1126-1135. PMLR, 2017. 12. A. J. Fisher, J. D. Medaglia, and B. F. Geronimus. Lack of group-to-individual generalizability is a threat to human subjects research. Proceedings of the National Academy of Sciences, 115-27, E6106 E6115, 2018. ISSN 00278424. DOI 10.1073/PIS.17119781115. URL https://www.pnis.org/content/115/27/E6106. 11. 13. S. A. Forbes, D. Beer, P. Gunasekaran, K. Lone, N. Bindel, H. Boutsalakis, M. Ding, S. Bamford, C. Cole, and S. Ward. Cosmic, Exploring the World's Knowledge of Somatic Mutations in Human Cancer. Nucleic Acids Research, 43D1, D805-D811, 2014. 14. N. Friedman, M. Goldsmith, et al. Discretizing Continuous Attributes While Learning Bayesian Networks. In ICML, pages 157-165, 1996. 15. L. Gahn, X. Yang, N. Narizetti, and F. Liang. Bayesian Joint Estimation of Multiple Graphical Models. In Advances in Neural Information Processing Systems, pages 9802-9812, 2019. 16. J. Guinea, R. Dienstmann, X. Wang, A. De Rennes, A. Schlicker, C. Sohnsen, L. Marissa, P. Repman, G. Nyamandanda, P. Angelino, et al. The Consensus Molecular Subtypes of Colorectal Cancer. Nature Medicine, 2111, 1350-1356, 2015. 17. S. A. Hart. Precision Education Initiative, Moving Toward Personalized Education. Mind, Brain, and Education, 10-4, 209-211, 2016. DOI 10.1111/m.12109. URL https://onlinelibrary.wiley.com/doi/abs/10.1111/m.12109. 18. T. Hasty and Artipshirani. Varying Coefficient Models. Journal of the Royal Statistical Society, Series B, Methodological, 55-4, 757-779, 1993. 19. F. Jabari and G. F. Cooper. An instance-specific algorithm for learning the structure of causal Bayesian networks containing latent variables. In Proceedings of the 2020 Siam International Conference on Data Mining, pages 433 to 441. Siam, 2020. 20. F. Jabari, S. Viswaswaran, and G. F. Cooper. Instance-specific Bayesian network structure learning. Proceedings of Machine Learning Research, 72 to 169, 2018. 21. F. Jabari, S. Viswaswaran, and G. F. Cooper. An empirical investigation of instance-specific causal Bayesian network learning. In 2019 IEEE International Conference on Bioinformatics and Biomedicine, BIBM, pages 2582 to 2585. IEEE, 2019. 22, D. Kahler and N. Friedman. Probabilistic Graphical Models, Principles and Techniques. MIT Press, 2009. 23, M. L. Cowger, M. G. Toon, G. Yuan, J. Quackenbush, and K. Glass. Estimating Sample-Specific Regulatory Networks. iScience, 14 to 226 to 240, 2019. 24, F. Ledoux, B. L. Eckhart, B. Lim, J. K. Litton, S. Mulder, F. Merrick Bernstam, A. M. Gonzalez Angulo, and N. T. Waino. Is the future of personalized therapy in triple-negative breast cancer based on molecular subtype? OncoTarget, 615, 12890, 2015. 25, K. Lee and X. Cao. Bayesian Joint Inference for Multiple Directed Acyclic Graphs. R14 preprint R14:2008.06190, 2020. 26, B. J. Lengerich, B. Aragam, and E. P. Crossing Learning Sample-Specific Models with Low-Rank Personalized Regression. In Advances in Neural Information Processing Systems, in Press, 2019. 27, N. I. Lindemann, P. T. Cagle, M. B. Beasley, D. A. Cheadle, S. Dachich, G. Jucone, R. B. Jenkins, D. J. Kwiatkowski, J. S. Saldivar, J. Squire, E. Thunison, and M. Ladany. Molecular Testing Guideline for Selection of Lung Cancer Patients for EGFR and ALK tyrosine kinase Inhibitors, Guideline from the College of American Pathologists, International Association for the Study of Lung Cancer, and Association for Molecular Pathology. Journal of Thoracic Oncology, official publication of the International Association for the Study of Lung Cancer, 87, 823 to 859, July 2013. ISSN 1556 to 1380. DOI 10.1097/JTO 0B013E318290868F. URL https://pubmed.ncb.nlm.nih.gov/2355237 https://www.ncb.nlm.nih.gov/pmc/articles/pmc4159960/. 28, T. P. Marikis, L. Benedetti, E. Foxall, J. Perner, M. Sarada, J. Lagergren, M. Howell, C. Yao, R. Fitzgerald, P. Scafidi, et al. Patient-specific detection of cancer genes reveals recurrently perturbed processes in esophageal adenocarcinoma. BioArxiv, page 321612, 2018. 12, 29, K. Ng, J. Sun, J. Hu, and F. Wang. Personalized Predictive Modeling and Risk Factor Identification Using Patient Similarity. AMIA Summits on Translational Science Proceedings, 2015 to 132, 2015. 30, C. J. Oates, J. Q. Smith, S. Mukherjee, and J. Cousins. Exact estimation of multiple directed acyclic graphs. Statistics and Computing, 26-4, 797 to 811, 2016. 31, A. P. Parikh, W. Wu, R. E. Curtis, and E. P. Crossing-Triegel, Reverse Engineering Tree Evolving Gene Networks Underlying Developing Biological Lineages. Bioinformatics, 2713, I-196 I-204, 2011. 32, J. Pensar, H. Nyman, T. Koski, and J. Corinder. Labeled Directed Acyclic Graphs, a Generalization of Context-Specific Independence in Directed Graphical Models. Data Mining and Knowledge Discovery, 29-2, 503 to 533, 2015. 33, V. Relli, M. Traratola, E. Guerra, and S. Alberti. Abandoning the Notion of Non-Small Cell Lung Cancer. Trends in Molecular Medicine, 25-7, 585 to 594, 2019. ISSN 1471 4914. DOI, https://doi.org/10.1016/j.molm.2019.04.012. URL http://sciencedirect.com/science/article/p/s147191419301017. 34, K. Sachs, O. Perez, D. Peer, D. A. Laufenberger, and G. P. Nolan. Causal Protein Signaling Networks Derived from Multi-Parameter Single-Cell Data. Science, 308 5721, 523 to 529, 2005. 35, B. Zayed, S. Panigrahi, and C. Euler. Causal Structure Discovery from Distributions Arising from Mixtures of DAGs. In International Conference on Machine Learning, pages 8336 to 8345. PMLR, 2020. 36, T. Scholl and J. Schmiduber. Meta-Learning. Scholarpedia, 5-6, 4650, 2010. 37, L. Song, M. Kolar, and E. P. Crossing-Keller, Estimating Time-Varying Interactions Between Genes. Bioinformatics, 2512, I-12836, 2009. ISSN 1367 4811, Electronic, 1367 to 4803, Linking. 38, P. Spertz, C. N. Glimore, R. Shines, and D. Heckerman. Causation, Prediction, and Search. MIT Press, 2000. 39, N. Stransky, A. M. Egloff, A. Dietward, A. D. Kostich, K. Sibielskis, A. Shivachenko, G. V. Krukov, M. S. Lawrence, C. Soons, A. McKenna, E. Scheffler, A. H. Ramos, P. Stojanov, S. L. Carter, D. Vogt, M. L. Cortez, D. Auclair, M. F. Berger, G. Saxena, C. Gijiksai, R. C. Onofrio, M. Parkin, M. Romps, J. L. Weisfeld, R. Arcivila, L. Wang, C. Rangel Escareno, J. C. Fernandez Lopez, A. Hidalgo Miranda, J. Melendez Zajba, W. Winkler, K. Ardley, S. B. Gabriel, M. Meyerson, E. S. Lander, G. Getz, T. R. Golub, L. A. Garraway, and J. R. Grandis. The Mutational Landscape of Head and Neck Squamous Cell Carcinoma. Science, 333 6046, 1157 to 1160, August 2011. 40, E. V. Strobel. Improved Causal Discovery from Longitudinal Data Using a Mixture of DAGs. In the 2019 ACM-SEEKed Workshop on Causal Discovery, pages 100 to 133. PMLR, 2019. 41, B. Thiessen, C. Meek, D. M. Chickering, and D. Heckerman. Learning Mixtures of DAG Models. R14 preprint R14:1301.7415, 2013. 42, O. Ursu, J. T. Neal, E. Shea, P. I. Takor, L. Jerby Arnon, L. Win, D. Dion, C. Diaz, J. Bauman, M. Mossad, et al. Massively parallel phenotyping of variant impact in cancer with perturbed seq reveals a shift in the spectrum of cell states induced by somatic mutations. BioArXiv, 2020. 43, R. K. V. Nayak, W. Kong, G. Valiant, and S. Kakade. Maximum likelihood estimation for learning populations of parameters. In International Conference on Machine Learning, pages 6448 to 6457, 2019. 44, L. Weekman, M. Sampson, M. Stempel, L. M. Jacks, S. M. Patil, T. King, and M. Morrow. Presenting features of breast cancer differ by molecular subtype. Annals of Surgical Oncology, 1610, 2705 to 2710, 2009. 13, 45, B. Zhang, C. Gaiteri, L. G. Badea, Z. Wang, J. McElwee, A. Podteleznikov, C. Zhang, T. Xie, L. Tran, R. Dobrin, E. Fluter, B. Klerman, S. Melquist, M. Narayanan, C. Suver, H. Shah, M. Mahajan, T. Gillis, J. Mysore, M. E. McDonald, J. R. Lamb, D. A. Bennett, C. Malani, D. J. Stone, V. Goodnissen, A. J. Myers, E. E. Shat, H. Newman, J. Jew, and V. Emelson. Integrated Systems Approach identifies genetic nodes and networks in late-onset Alzheimer's disease. Cell 153-3, 707, 720, April 2013. ISSN 0092286674. DOI 10.1016/j.cell.2013.03.030. URL http://europepc.org/articles/pmc36777161. 46, X. Jung, B. Aragam, P. K. Ravikumar, and E. P. Crossing DAGs with NOTEARS, Continuous Optimization for Structure Learning. In Advances in Neural Information Processing Systems, pages 9472 to 9483,